A species of deer is to be introduced into a forest, and experts estimate the deer's population will grow according to P of t equals 100 deer times 2 to the t, where t is time in years after the deer are introduced. How long does it take for the deer population to double? To solve this, we want to start with the original equation. P of t equals 100 times 2 to the t. And we'd now like to realize that 100 deer is the initial population at time 0. How do we know this? Well, imagine t was 0. If t was 0, then we'd have 2 to the 0, which is 1, and then the population would be 100. So in order to get the population to double, all we have to do is just put a 200 over here. P stands for the final population after time t. And now we can solve this equation for t. Doing it requires that we do the reverse order of operations. We're going to undo this multiplication before we undo the exponent. So let's divide by 100 on both sides, giving us 2 equals 2 to the t. And now it's apparent what the answer is. T is 1. But the way that we technically solve this is by taking a natural log of both sides. The reason we take the natural log of both sides is because logs have this property where if the thing in the argument of the log is being raised to a power, then that power could come down in front and you'd still get the same answer out of this as you would have got in the expression above. We'll divide by ln2 on both sides and get that t is 1. So it'll actually take 1 year to double. In B, a species of deer is introduced into a forest, and experts estimate this time the deer's population will grow according to 200 times 4 to the t. How long does this population take to double? Well, once again, let's start with the original equation. And remember that the number attached to the base of the exponent is the initial population. So we want the population to double to 400. Divide by 200 on both sides. Get 2 equals 4 to the t. And we can solve this one just by taking a log of both sides and then bringing the t down in front. And finally, we'll divide by ln4, revealing that t is ln2 over ln4. Which is 0.5 years. So that was a faster growing population. In this last example, 54 rabbits are released in an isolated area free of predators at t equals 0. Their population grows exponentially, and after 2 years, it's estimated that their population is now 216 rabbits. What would the population grow to after another 3 months? Alright, so let's go ahead and create an equation of our own of the form AE to the RT. Now, we know the initial population. It's 54 rabbits at t equals 0. So, when we have e to the 0, that's just 1. So actually 54 is our a value. Now what we'll do is write that in our function. But at this point, we need to know what R is. So let's use the other information given. They said after 2 years, we'd have 216 rabbits. So we'll set P equal to 216. That's the final value of the population. And they said that this would happen after 2 years. Like before, we'll solve for an exponent, but this time it's R that we're looking for. Take an ln on both sides. That gives us ln 4 equals 2r because ln and e are inverses. Now we have r equals ln 4 over 2. Now what will we do with this? We want to finish constructing our function. This is our function describing the rabbit's population growth. They start at 54, and then as time goes on, they grow according to an r of ln 4 over 2. Now we can use this formula for the purposes of prediction of how many rabbits there'll be after 3 more months. Our time t is supposed to be in years, though. At least that's how we had used it previously. So we're going to have to figure out how many years 2 and 3 months is. Let's see, it would be 2.25 years. 3 months being a quarter of a year. All right, let's plug that in on calculator. Approximately 257 rabbits.